Hey everyone, welcome to this explainer. Today we are going on a really fascinating journey to demystify the complex and honestly rapidly evolving world of artificial intelligence. We're going to trace the entire path, starting all the way down at the foundational physical hardware limits, right up to the massive societal implications. So whether you're already deeply entrenched in the tech world or you're just trying to make sense of the latest headlines, this structured breakdown is going to clarify exactly how we get from microscopic silicon chips all the way to shifting global power dynamics.
Okay, so here's our roadmap for today. 1. Growth, history, and hype. 2. How AI models learn. 3. Understanding emergent AI behaviors. 4. The path to the singularity. And finally, 5. Power, governance, and control. Let's just dive right in.
All right, starting with Section 1, Growth, History, and Hype. Look, to really grasp rapid technological change, we first have to anchor ourselves in the physical limits of computing and how we as a society react to it. Before we can even talk about intelligent software, we absolutely have to talk about the physical engines making it all possible.
Because the foundational engine driving all this massive technological capability, it isn't magic, it's hardware. Specifically, Moore's Law. It's this observation that every 2 years or so, the computing power we can cram onto a single microchip literally doubles. This compounding exponential growth explains exactly why AI capabilities seem to be accelerating at such a staggering pace right now. It is a very grounded physical reality that essentially sets the speed limit for everything else we're going to talk about today.
But here's where it gets interesting. We strictly have to separate that predictable hardware progress from human emotion. Check this out. On the left, Moore's Law gives us this relatively smooth, steady exponential curve. But on the right, the hype cycle is just a total roller coaster. Think back to the early days of the internet or even virtual reality. You get this intense, burst-like initial excitement, massive exaggeration, and then sudden disillusionment before things actually stabilize. As a society, we tend to wildly overreact to new tech in the short term while completely underreacting to its true massive impact in the long term.
Think about the Industrial Revolution for a second. It completely moved humanity from muscle power to machine power, shifting economies entirely using water and steam. Well, today, we are crossing a strikingly similar threshold, but instead of steam, it's exponential computing power acting on human knowledge itself. This current wave of compounding capability is poised to reshape our world just as fundamentally. Which brings us to Section 2, How AI Models Learn. Let's zoom out from the physical hardware and get into the actual software mechanics of how these systems build their intelligence.
So think of inductive bias kind of like giving the AI a basic rule of thumb. Without it, an AI trying to learn from scratch would be completely paralyzed by infinite possibilities, right? An AI can't possibly infer every single rule of the universe just from seeing a few examples. So inductive bias acts as this necessary mathematical constraint. It guides the algorithm toward a particular type of solution so it can actually generalize its knowledge and handle brand new unseen data.
Now, the really crucial point here is that we must absolutely separate the mathematical assumptions that make learning possible from the human flaws that create prejudiced outputs. When you hear the word bias in the news regarding AI, they are almost always talking about the broken funnel on the right, systematic errors creeping in because the human-provided training data itself was flawed, skewed, or unrepresentative. Basically, inductive bias is a mathematical requirement, data bias is a human failure.
Now let's talk about scaling laws, and wow, this is incredibly powerful. It's an empirical observation that if we predictably increase 3 main resources, model size, dataset size, and compute power, model capabilities don't just improve randomly, they improve in a highly predictable, reliable manner. We feed the system more parameters, more data, and more compute, and performance just shoots up across the board, setting the stage for what happens next.
And let's explore exactly what happens next in Section 3, Understanding Emergent AI Behaviors. Because as we scale up those inputs, we cross a threshold where these models stop just doing what they were explicitly told to do.
It poses a really fascinating question in the field of AI. What actually happens when we push the scale of these systems to the absolute extreme? If we keep following those scaling laws, throwing more data and processing power at it, do we just get a faster calculator, or does something else happen entirely?
Well, suddenly, a massive model might develop a brand new skill, like detecting sarcasm or human sentiment. This is called an emergent property. And the astonishing part? The developers themselves never explicitly programmed the AI to do that.
It just suddenly developed the skill entirely on its own as a byproduct of its sheer complexity in analyzing billions of human interactions. The behavior emerges from the scale rather than from direct instructions.
To wrap our heads around this dual reality, researchers contrast observing mysterious outputs with mapping the inner workings. Emergent properties are the magic we see happening on the outside. Mechanistic interpretability, on the other hand, is the painstaking work happening on the inside. It's researchers basically acting like digital neuroscientists, peering deep inside the brain of the neural network to understand exactly how and why it's producing those specific emergent results. Actually, scratch that. Let me pause right here for a second and make sure we don't confuse these impressive technical capabilities with actual subjective consciousness. Just because a system displays complex, unexpected behaviors, like chatting with you convincingly, does not mean it possesses a subjective awareness of its surroundings. It is incredibly capable mathematics mimicking understanding, not a living mind suddenly waking up.
Which brings us to Section 4, the path to the singularity. Having seen how scale triggers these unexpected abilities, let's zoom out even further to examine the theoretical trajectories of where all this compounding power might ultimately lead us.
Check out this theoretical feedback loop. It's called recursive self-improvement. Imagine an AI smart enough to rewrite its own source code. It makes a slight enhancement. Now, that smarter version rewrites the code again, but better and faster. This continuous, accelerating loop of self-enhancement could lead to iterations that quickly surpass human comprehension, evolving entirely without our input.
If that loop of self-improvement truly takes off, it leads directly to the singularity. This is essentially a theoretical point of no return. It's the moment when technological growth irreversibly outpaces our human ability to control or even understand it, fundamentally and permanently altering human civilization. Researchers use this concept to frame the ultimate risks of rapid, uncontrollable capability compounding.
Now, we are presenting these intensely polarized views not as inevitable prophecies, for sure, but as necessary framing devices for thinking objectively about trajectories and risk. On one hand, you have the AI doomers, individuals heavily forecasting severe negative outcomes or dystopian societal collapse. On the other hand, you have those focused purely on optimistic acceleration and profound technological benefits. In this explainer, we aren't taking a side. Rather, we're highlighting that understanding this very debate is absolutely crucial to understanding the modern AI landscape itself.
And right in the middle of all this prediction is Moravec's paradox. This paradox is a brilliant reminder that machine progress does not have to mirror human intuitions about what should be easy or hard. A computer can easily calculate multivariable calculus or crush a grandmaster at chess. But ask a billion-dollar robot to fold your laundry or walk up a flight of stairs, it suddenly looks like a clumsy toddler. Simple physical intuition is still monumentally difficult for machines.
All right, final stop, Section 5, Power, Governance, and Control. Let's zoom all the way out to humanity, exploring how these autonomous capabilities collide with global economics and human psychology. Because look, advanced AI isn't just a shiny new app on your phone, it's a foundational layer, much like electricity or the internet, that will run beneath everything we do. It's what we call a horizontal enabling layer. It is not limited to a single domain like healthcare or finance. It possesses foundational capabilities that will essentially transform every single industry concurrently.
Ultimately, this horizontal layer is colliding with human reality in 4 key ways. Nations are battling for sovereignty, fiercely trying to maintain control over their tech destinies. Barriers of entry are shifting wildly, collapsing for small creators who can now do the work of 50 people, yet skyrocketing for the massive actors who can actually afford to build these foundational models. And psychologically, we are totally caught between a negativity bias, heavily fixated on doom, and a massive FOMO, fear of missing out, driving panicked billion-dollar investment trends.
So to conclude this explainer, I'll leave you with this final, massive question. The physical hardware and the software, they're clearly evolving on a steep exponential curve. But is our capacity for human governance, regulation, and psychological adaptation evolving fast enough to keep up? It's a question that researchers, policymakers, and everyday citizens will have to answer together in the coming years. Keep exploring, and thank you so much for joining me.